Hi, I'm Dick Miller, a corporate pilot and FAA designated pilot examiner. I'd like to introduce you to Chelton's Flight Logic EFIS, the world's first certified synthetic vision flight display system. When I'm not giving FAA flight checks, I fly one of these aircraft. It's hard to believe, but I can tell you from experience that the capabilities of the Flight Logic EFIS exceed what these aircraft have on their flight decks. The Flight Logic EFIS features forward-looking, real-time 3D terrain, GPS WAAS, a 3D predictive flight director, an integrated FMS, a master voice warning system, and a digital flight recorder. It also performs virtually all the functions found on a traditional high-end EFIS. Furthermore, it will interface with virtually any autopilot ever made and provide it with digital roll steering for hands-free instrument procedures. The Flight Logic EFIS was designed with the IFR pilot in mind. Originally conceived by a Navy carrier pilot during daily operations in the Gulf War, the system is modeled after those found in modern warplanes. Military systems are both highly integrated and highly automated, yet the pilot is always kept in the loop with advanced display symbology. Furthermore, flight information is performance-based, meaning it provides an indication of what the airplane is actually doing right now, not just where it is pointed. Instead of replicating traditional mechanical instruments, the Flight Logic EFIS paints an informational picture of what's going on. Providing the pilot with useful information rather than just more data is the key to increasing situational awareness and, in turn, safety. With this in mind, Chelton set out to create a system that will prevent pilot error, which accounts for 85% of all accidents. Giving the pilot VFR visual cues, regardless of the weather outside, is the key, and synthetic vision does just that.
Welcome to the world of synthetic vision and truly advanced flight instrumentation. This video has been created to introduce you to the Flight Logic EFIS and prepare you to operate the system. It includes a system overview, a description of symbology and features, operating procedures, some sample flights, and some pointers to help you get the most out of the system. By the end of this program, you will be able to identify the major components of the system, identify the elements on the screens, create and edit flight plans, work with an active flight plan, set up and fly instrument procedures, navigate using Highway in the Sky, and control the display of information on the system. After you have watched this program, Chelton recommends that you receive a few hours of dual instruction in your own aircraft from a Chelton authorized flight instructor. A list of authorized instructors can be found at our website at www.cheltonflightsystems.com. Chelton also recommends that you fly a variety of complete instrument approaches in VFR conditions to become familiar with the system and then raise your personal minimums until you are completely comfortable with it. Let's start with the basic components. On the panel, you will have one or more displays. If you have a single display, it will be configured as a multi-function display or MFD for supplemental information only, and will show both the primary flight display or PFD and a navigation display or ND. The ND can be configured as a moving map, an HSI, a dedicated traffic display, or a dedicated weather display. If multiple screens are installed, the first one will be fixed as a PFD, and all remaining displays will be MFDs. The displays require no special maintenance other than periodic cleaning of the screens with an appropriate LCD screen cleaner, which can be found in stores that sell computers. The displays will operate reliably from -20 to 50 degrees Celsius. Storage temperatures range from -55 to 85 degrees Celsius. The displays are thermally protected and cannot damage themselves by overheating in the event of loss of cooling. They are water resistant, but care should be taken not to spill liquids like coffee or soda directly onto them. The screen itself is quite rugged, although it can be scratched by metal objects like a pen. Finger touching will not damage the screens, but will leave oil residue that attracts dust, resulting in the need for frequent cleaning. Care should be taken to prevent long-term exposure to direct sunlight. With little attention, they will last the life of the aircraft. The screens display data from a variety of discrete components. Included with the system are an attitude and heading reference system, an air data computer, and a GPS WAAS receiver. The Attitude and Heading Reference System, or AHRS, senses attitude of the aircraft and sends it to the display as roll, pitch, and yaw data. It also sends magnetic heading. The AHRS is a strap-down design, meaning it has no moving parts. It is non-tumbleable and non-precessing. Heading is constantly updated through an integral magnetometer. The AHRS mounts remotely in the aircraft. It requires no special maintenance and will operate from -40 to 70 degrees C. Storage temperature ranges from -55 to 85 degrees C. Although the basic system includes an AHRS, any existing AirRink 429 TSO'd attitude and heading source is compatible and approved for use. The displays receive airspeed, altitude, outside air temperature, and fuel flow from an air data computer, or ADC. The ADC is connected to the aircraft's original pitot-static system. An outside air temperature probe is mounted on the aircraft's exterior skin, and, if available, either stock or aftermarket flow transducers send fuel flow data to the ADC for totalizer functions on the navigation display. The ADC needs no routine maintenance. The ADC is unaffected by temperatures encountered by aircraft, but may require up to 3 minutes to reach full accuracy in very cold weather. An advisory flag will be displayed on the screens until the ADC has reached operating temperature. Although the basic system includes an ADC, any existing AirRink 429 air data computer is compatible and approved for use. A GPS WAAS receiver completes the basic flight logic system and provides position, integrity monitoring, ground speed, and Zulu time. The receiver itself is a small remotely mounted box that receives and processes the GPS and WAAS satellite signals through an antenna mounted on top of the aircraft. WAAS utilizes a network of precisely surveyed ground stations to receive the GPS signal and compare the indicated position with the known surveyed position. The difference between these two is the position error, which is transmitted back up to the WAAS satellites, which in turn broadcast it to GPS WAAS receivers. The receiver then applies the correction to the aircraft's indicated position, resulting in very precise positioning and integrity monitoring. If the position error is too large, the GPS signal is considered suspect by the receiver and the EFIS provides a caution. This integrity monitoring is not possible with non-WAAS GPS receivers, leaving the pilot with no indication as to whether their GPS position is correct or not. Errors can come from electromagnetic disturbances, like solar flares, poor satellite triangulation geometry, or an echo effect of the signal bouncing off terrain beneath the aircraft called multipath. The GPS also provides fault detection and exclusion, or FDE, to detect and then ignore data from unreliable satellites. If WAAS or FDE is available, the GPS is approved for standalone sole source navigation for all IFR en route and non-precision approach procedures, including RNAV and LNAV Barrow VNAV approaches. If the system is displaying a GPS caution flag, an approach cannot be continued past the final approach fix, and you should revert to another navigation source. Please refer to the Pilot's Guide for additional information on GPS WAAS performance requirements. The GPS requires no routine maintenance and is unaffected by temperatures encountered by aircraft. The Flight Logic EFIS may be installed with an Analog Interface Unit, or AIU. The AIU acts as an interpreter between the EFIS and conventional analog avionics, like VHF nav radios and autopilots. It can simultaneously bring in signals from two VOR localizer glide slope receivers, a flight director, an ADF, a radar altimeter, and a marker beacon receiver. It supports all conventional nav modes. It also provides digital and analog roll steering capability to virtually any autopilot, allowing hands-off tracking of any published procedure, including procedure turns, arcs, holding patterns, missed approach procedures, and even holding pattern entries. The AIU is not affected by temperatures encountered in aircraft, and it requires no routine maintenance after the initial configuration. The EFIS can also display weather and traffic from a variety of sources, including the Ryan TCAD and the L3 Skywatch and StormScope, and the Garmin Mode S transponder. A number of data link weather interfaces are being developed as well. A fast-slow indicator may be displayed from an AirRink 429 angle of attack computer. Additional interfaces are being added regularly. During installation, a number of aircraft-specific values like V-speeds, glide ratio, fuel capacity, and landing gear configuration are programmed into a limits file for use by the system. The limits file is stored in a special chip located in the display's mounting tray. Any display can be placed in any position in any aircraft at any time. This allows the displays to be replaced without the need for reprogramming, thereby expediting service and reducing cost. Before flying with your FlightLogic EFIS, be sure you understand these warnings. Do not use this system for terrain following flight. Do not attempt to navigate using the terrain depiction. Always adhere to published instrument approach procedures in instrument conditions. Skyway Symbology does not provide precision approach guidance, nor does it guarantee terrain separation. It remains the pilot's responsibility to provide self-separation from terrain. Do not continue an instrument approach beyond the decision height or below the minimum descent altitude unless the landing environment is visible, according to the Federal Aviation Regulations. WAS or fault detection and exclusion, FDE, must be available at the final approach fix to continue an instrument approach. Do not engage in instrument flight unless you are instrument rated and current, and your aircraft meets the IFR requirements specified in the Federal Aviation Regulations. There are many towers, antennas, and obstructions that are not in the database. The VFR approach function does not provide terrain or obstruction clearance. Extreme care should be taken when using the VFR approach function at night or in marginal VFR conditions. If you do not understand any of these warnings, consult a Chelton authorized instructor for clarification. The FlightLogic EFIS features an integrated terrain awareness and warning system, or TAWS. There are 3 different classes of TAWS: A, B, and C, and all use the same terrain database used in ground proximity warning systems in airliners. Class B and C TAWS perform the following functions: Forward-Looking Terrain Alert, or FLTA, which scans the space the aircraft is flying into for threatening terrain, excessive rate of descent, premature descent, and altitude loss on climb-out, and a 500-foot call-out on approach. Class B and C differ only in the point at which an alert is given. Class C TAWS is slightly less sensitive than Class B, thereby minimizing nuisance alerts in piston-powered aircraft, which typically fly lower and slower than turbines. Class B TAWS is for turboprops and small jets, and is more sensitive to terrain to account for the higher speeds and higher operating altitudes. Class A TAWS has all the functions of Class B and C TAWS and adds alerts for excessive glide slope deviation and excessive closure rate to terrain. When installed in helicopters, the EFIS provides Class A or B helicopter TAWS functions, which allow for operation closer to the ground without generating nuisance alerts. Helicopter Class B features only FLTA and altitude loss on climb-out functions. Helicopter Class A features all TAWS functions except premature descent alert and the 500-foot call-out. All TAWS classes also include man-made obstructions in their search envelopes. Class A TAWS adds a glide slope cancel switch to disable the glide slope deviation warning, and helicopter systems add a low-altitude switch that enables operation in close proximity to the ground while retaining alerting functions and minimizing nuisance alerts. TAWS alerting is divided into cautions and warnings. Cautions are displayed as yellow terrain on the moving map, a yellow caution flag on all screens, and an enunciation of
Caution. Terrain. Caution. Terrain.
Upon receiving a TAWS caution, the pilot should immediately refer to the moving map display to identify the threatening terrain and use extreme caution if choosing to proceed. Ignoring a TAWS caution may result in a TAWS warning. A TAWS warning generates red terrain on the moving map, a red warning flag on all screens, and a voice warning that repeats until silenced by the pilot or alleviation of the terrain threat.
Terrain. Terrain. Pull up. Pull up.
TAWS warnings require immediate pilot action to avoid impacting terrain. Red and yellow TAWS colors on the map are shown with a degree of transparency, allowing the pilot to identify terrain contours in order to perform an evasive maneuver. Pilots are authorized to deviate from any ATC instruction when reacting to a TAWS alert. TAWS is more sensitive during en route flight when the aircraft is flying fast and the pilot is expecting to have adequate terrain separation. When an approach is selected, TAWS is desensitized since the aircraft will be slower and closer to the ground. All classes of TAWS have an inhibit switch located near the PFD, which disables the audio alerts and flags. The threatening terrain display remains fully functional on the moving map. TAWS should only be inhibited in VFR conditions when flying intentionally close to the ground. TAWS should not be inhibited during instrument conditions. Class A TAWS adds a glide slope cancel switch to inhibit the glide slope warning for the duration of an ILS approach. This is a momentary switch that only needs to be actuated once during the approach. Helicopter TAWS adds a low-altitude mode switch to further reduce sensitivity to terrain for continued intentional, very low-altitude operations. Terrain decluttered manually by the pilot is indicated by a green X, and all TAWS functions remain enabled. When terrain information is determined by the system to be unusable, it is removed and indicated by a red X, and the FLTA function is disabled. All other TAWS functions remain enabled as long as the system can compute a valid AGL altitude. Please read the detailed TAWS description in the display symbology and appendix sections of the Pilot's Guide for additional information. The TAWS voice warnings are part of an integral voice warning master caution system. Auditory enunciations are provided for a variety of conditions that require pilot attention. Examples include exceeding speed limitations, altitude deviation, undesirable fuel situations, conflicting traffic, sensor failures, and a variety of other conditions. On a perfectly flown flight, the only voice enunciations provided should be the level off reminder during climbs.
Level off. Level off.
And the 500-foot call-out on final approach.
500. 500.
However, if you forget to put the landing gear down or set the altimeter to 29.92 when climbing into the flight levels, the system will alert you. Chimes and tones are used to call attention to non-critical conditions, such as GPS mode change and timer expiration. Some cautions, warnings, and advisories are prioritized based on level of severity. Some are not. Audio output volume is automatically adjusted, with warnings being the loudest. Warnings shown in red demand immediate pilot action. Cautions shown in yellow require pilot attention, and advisories shown in green are for informational purposes. Caution, warning, and advisory flags are always stacked in the lower left corner of the displays and are presented with the most critical alert on top. Cautions are enunciated twice, while warnings repeat until acknowledged by the pilot or the condition is corrected.
Fuel low. Fuel low.
When the mute button on the yoke or near the PFD is pushed, enunciations are silenced immediately. The flags are displayed until the condition is corrected. A Master Caution System interactive training aid is available for additional familiarization. It provides samples of all of the system's enunciations, the conditions that generate them, and the proper pilot action. You may also download the Master Caution System Training Aid from our website. It is a large file, so it requires a high-speed internet connection. If you don't have a high-speed connection, it is available on CD-ROM for a nominal fee by contacting us. The terrain database is stored in the displays along with two others, the Jeppesen nav data and the FAA's obstruction data. For speed and redundancy, all databases are stored in each display. Terrain is stored on a removable card which can be changed by an avionics shop or your airframe mechanic. A single card contains a large section of the globe. For example, all of North America is stored on a single card for seamless terrain depiction from Anchorage, Alaska to the Bahamas and from Hawaii to Greenland. If flying to another region of the globe, the terrain card may be replaced at some point along the route. Flying beyond the boundaries of the terrain database will result only in the loss of terrain-related functions like TAWS and will be indicated by a red X. Navigation and obstruction databases, on the other hand, are updated every 28 days and posted on the Chelton Flight System's website for downloading. These updates may be purchased individually or as an annual subscription. The files are downloaded from the website to a smart media card. Please complete the brief database updating tutorial on the website before updating your system. Updates are also available by mail. With the power off, insert the card into the slot in the front of the screen. Upon power up, a list of options will be provided. Use the control knob to select the Update Database option. Turn to scroll, push to enter. Follow the screen prompts to complete the procedure. Switch the power off and remove the card. Inserting or removing the card with the power on will not damage the displays, but may render the card unreadable. This procedure is repeated for each display. One database subscription updates all displays in an aircraft. Many pilots are familiar with HUDs, or heads-up displays, found in modern military aircraft. Using a combination of military and transport category elements, the FlightLogic PFD superimposes HUD symbology over a 3D synthetic view of the outside world in order to give the pilot many advantages of a HUD without the weight and cost. In fact, HUDs are the most useful when the outside world is visible through them, whereas Chelton's synthetic vision provides 40 miles of visibility in all conditions. Indicated airspeed is on the left in both tape and digital formats. The tape is colored with the range and speed markings of a conventional airspeed indicator. Important speeds traditionally not shown on airspeed indicators, like VX, VY, and VA, are indicated as well. Takeoff and landing reference V speeds may also be displayed on the tape if desired. Best glide speed, based on gross weight, is shown as a green dot. For enhanced low-speed awareness, the tape is colored red below VSO. To the left of the airspeed tape is an airspeed trend that shows what the speed will be in 6 seconds. A bug can be used to set target airspeed, and the target speed is displayed above the tape. Bugs can also be set for V1, VR, V2, and VREF. If appropriate, Mach number is displayed near the top of the airspeed tape. Altitude is displayed in the same fashion on the right. The tape is gray above ground level altitude and brown below. A target altitude bug may be set manually by the pilot. A minimum altitude bug can be set by the pilot as well. When set, target and minimum altitudes are displayed above the altitude tape. Target altitude is bracketed above and below, while the minimum altitude only has a line beneath it, just like on approach charts. To the right of the altitude tape is the VSI. It points up in a climb and down in a descent. The rate is displayed in hundreds of feet per minute at the end of the pointer. The directional scale extends across the entire top of the display. The white pointer indicates heading. The green diamond represents GPS ground track. The magenta star is the bearing to the waypoint and is only shown when there is an active waypoint. Aligning these two symbols will take you directly to the waypoint. If the waypoint symbol is beyond the visible portion of the directional scale, a magenta arrow points to it. The heading pointer has a white bar below it that moves laterally to indicate a slip or skid. For systems installed prior to version 5, a mechanical slip indicator was utilized. The small winged V is called a waterline and indicates pitch attitude against the pitch scale, just like a conventional attitude indicator. Unlike a conventional attitude indicator, The waterline is not adjustable. It is aligned with the longitudinal axis of the aircraft and may therefore be slightly above the artificial horizon line in level cruise flight. The pitch scale is used to measure angle above or below the artificial horizon. The pitch scale is automatically decluttered above and below 10 degrees from the horizon. However, if needed, the pitch scale is drawn at least 10 degrees ahead of the waterline as pitch increases. A zenith symbol is displayed at 90 degrees up, and a nadir symbol is shown at 90 degrees down. The pitch scale is graduated in 5-degree increments with a major line every 10 degrees. Small tick marks on the major lines point toward the horizon. The artificial horizon is the thin white line extending the entire width of the display. As with all conventional attitude indicators, the artificial horizon on the EFIS indicates the aircraft's altitude extended ahead. It does not depict the Earth's horizon. That's why it's called an artificial horizon. Think of it as a zero-pitch line. This is an important distinction that will be illustrated later. A conventional bank angle scale with marks at 10, 20, 30, 45, and 60 degrees is shown anytime the bank exceeds 2.5 degrees. It is automatically decluttered during relatively level flight, and it's dampened to minimize nuisance flashing on and off in turbulence. The pilot may override the auto declutter option and set the bank angle scale to display full time if desired. Together, the waterline, pitch scale, artificial horizon, and bank scale make up a traditional attitude indicator. In its most basic form, the PFD is a simple attitude indicator with airspeed, altitude, and DG all combined on a single display. Time for a quick quiz. You'll be given 1 second to view the following instrument and determine what the aircraft is doing at full power. Ready? If you said the aircraft is climbing, you're in the vast majority. Let's add a second instrument. Now it is clear that the aircraft is descending. This type of misinterpretation is common in a demanding flight environment and can lead to spatial disorientation or loss of aircraft control, two leading causes of accidents. This brings us to one of the most important features of the Flight Logic EFIS. Moving freely around the PFD is an airplane-shaped symbol called a flight path marker. To pilots without military or airline backgrounds, the flight path marker may be a new concept and may seem confusing at first. In reality, the flight path marker is extremely simple. It depicts where the aircraft is going regardless of attitude or wind. A conventional attitude indicator and DG, on the other hand, simply shows where the aircraft is pointed. Where the aircraft is going, not where it is pointed, determines the outcome of instrument approaches and other tasks like waypoint navigation, clearing terrain, and avoiding obstacles and other aircraft. The flight path marker moves left and right relative to the waterline to account for the difference between heading and ground track. It will laterally follow the green diamond on the directional scale. Here we see it displaced to the left, which means the ground track is to the left of the heading. This is caused by a crosswind from the right. Conversely, when displaced to the right, the nose is pointed into the wind from the left. It moves up and down relative to the artificial horizon line according to instantaneous VSI. When the flight path marker is above the horizon, the aircraft is climbing. When it is below the horizon, the aircraft is descending. It is the center of your scan, so the pitch scale moves with it as a climb-dive reference. If the flight path marker is aligned with the 5-degree pitch scale line, the aircraft is climbing at 5 degrees. Here we are in a climbing left turn. Here we are in a level right turn. It is easily interpreted, and there is no need to correlate another instrument to determine what the aircraft is doing. Remember, the flight path marker is where the aircraft is going. Factors that affect behavior of the flight path marker, like wing loading, vary from aircraft to aircraft, so it can be tuned to optimum performance in your aircraft. Ideally, the flight path marker should be lively enough to enable holding altitude in steep turns, yet damped enough so that it remains useful in turbulence. This adjustment is made by varying the ratio between static VSI and instantaneous vertical acceleration, and can be made in minutes by your dealer. It may take several flights to get it adjusted properly for your aircraft and preference. Since the flight path marker moves left and right to account for crosswind, occasionally in strong winds, the pitch scale will cage, meaning it returns to the center of the screen to avoid cluttering the airspeed and altitude tapes. The flight path marker continues to function normally, but the ring of the symbol is removed, leaving only the wings and tail to minimize clutter. A grayed-out ghost of the flight path marker remains attached to the pitch scale to provide a climb-dive angle reference. For navigation purposes, always use the white flight path marker. As part of the system's enhanced low-speed awareness, a pitch limit indicator, shaped like a hat, appears above the flight path marker at 20 knots above the gross weight clean stall speed and moves down toward the flight path marker as speed decreases. At 5 knots above clean stall, the pitch limit indicator, or PLI, turns red. The PLI is automatically inhibited below 50 feet AGL. The PLI may be permanently inhibited during installation if not desirable for your aircraft. Attached to the left wing of the flight path marker is a G meter. The G meter is only displayed when the G loading exceeds 0.2 G either way from 1 G. Like the bank angle scale, it is dampened to prevent nuisance flashing in turbulence. Immediately below the flight path marker is the AGL altitude. It is shown anytime the aircraft is below 2,500 feet AGL and is based on radar altimeter altitude, GPS altitude minus terrain elevation, or barometric altitude minus terrain elevation, in that order, depending on validity of sensor input and the accuracy of the GPS signal. The source being used is indicated by an R for radar, a G for GPS, or a B for barometric. Like other GPS navigation systems, the FlightLogic EFIS allows the pilot to navigate directly to any waypoint. Unlike other systems, however, the FlightLogic EFIS displays these waypoints directly on the PFD. The active waypoint is shown on the PFD as a magenta hoop with a radius of 200 feet. If the waypoint is associated with something on the ground, like a VOR station, a line will extend from the hoop down to the ground facility, which will be shown as an X. If the waypoint is not associated with anything on the ground, an airway intersection for example, it is shown simply as a hoop. During a flight, the waypoint hoops are connected with the highway in the sky, also referred to as the skyway. The highway in the sky, or HITS, forms a 3D tunnel that leads the pilot through each waypoint from departure to the landing runway, including any turns, climbs, or descents. The HITS boxes measure 320 feet high by 400 feet wide and are spaced every 2,000 feet along the route. For comparison, a localizer is 700 feet wide at the runway end. 5 HITS boxes are always shown ahead of the aircraft to provide the pilot with anticipation of upcoming maneuvers. The pilot always knows what is coming next because the HITS boxes begin to turn, climb, or descend 2 miles ahead of the aircraft. The HITS can be thought of as a predictive flight director. A conventional flight director graphically tells the pilot,
Bank left now.
The HITS graphically tells the pilot,
You are approaching a left turn.
This may sound like a subtle distinction, but a visual depiction of impending turns is a gigantic leap forward in flight guidance technology. The HITS Predictive Flight Director provides guidance through all published instrument procedures, including course reversals, arcs, missed approaches, holding patterns, DPs, and stars. The system even calculates the correct entry to a holding pattern, whether parallel, teardrop, or direct, and provides HITS guidance to fly it. If an altitude is specified, the waypoint hoop is shown as the desired altitude. Flying the flight path marker through the hoop will take the aircraft directly over the waypoint at the desired altitude. Skyway box altitude is controlled by the desired altitude, aircraft climb performance, and climb-descent angle setting. Desired altitude is set by the target altitude bug, shown in white, or a VNAV altitude, shown in magenta. If no desired altitude is set, then the Skyway boxes just go up and down with the aircraft's altitude. The VNAV function provides pre-programmed altitudes for all waypoints in the active route, which are set manually by the pilot, loaded from the Jeppesen nav data for procedures, or calculated by the EFIS. When one waypoint in the active route is assigned a VNAV altitude by the pilot or the nav data, the EFIS automatically fills in altitudes for the rest of the waypoints. Climb and descent angle settings are controlled individually with a resolution of 0.1 degree using the VNAV CDA function in the Bugs menu. When the active waypoint is part of a procedure, the system automatically sets the VNAV altitudes from the navigation database when they are coded by Jeppesen. Active waypoint crossing altitudes may be individually selected as well to comply with ATC or flight planning requirements. For en route climbs, the Skyway boxes are presented using one of three methods: a climb angle emanating from the aircraft's present position, known as aircraft referenced, a dynamic climb angle emanating backward from the next waypoint target altitude, known as geo-referenced forward, or the VNAV climb angle setting emanating forward